Hello everyone, welcome back. Today, I want to make a short video just explaining some general trends of the graphs of conic sections. So our goals in this video are to understand how conic sections are created and also be able to tell the type of conic section graph of an graph of an equation, be able to tell, what type of conic section graph and equation will produce based on some key features. And here to essentially be able to determine, distinguish between the different conic sections based on some things about the equation. And also we'll talk about how to use desmos.com, for example, as one website we can use to not only graph any kind of just functions, but also equations themselves, which is often something that some graphing calculators won't do. This is a very useful feature. A lot of times you're trying to figure out what something is or some basic features of it. So first off, a quick review of the conic sections. So the conic sections are created. So if you take two cones, circular cones, put them point to point like this, then if you take a plane, so imagine like a piece of paper cutting down across it, depending on how you cut across it, you'll get four different types of what are called conic sections. Actually, start with the most familiar first. Start with a circle first. So if you cut basically perpendicular to, think about the points where the cones are pointing each other up and down. If you cut straight across like this, perpendicular to that direction, then you get a circle. At each point, cut anywhere along that, you get a circle. Except right here at the very point, you choose just a point. Now, if you cut at an angle instead of cutting perpendicular to this axis here, then you get what's called an ellipse. And once again, depending on where you cut it, you can get a kind of a longer ellipse or even a shorter ellipse. And so what this also indicates, the base of a circle is essentially a type of ellipse where essentially you just cut straight across. So that's kind of what distinguishes these two features, these two conic sections from the rest, is that basically they're closed features. And depending on where you cut, you can either, if you cut perpendicular straight across, you get a circle. If not, you get an ellipse. Now, if you cut it in such a way that one end is open, doesn't close on itself, doesn't essentially can't come back to the starting point. If you go around it and trace it out in the path, it doesn't come back to the starting point. In this case, you get a parabola. Okay, so you can see it doesn't connect. These ends don't connect to each other, but you cut across, you get a parabola. And then if you actually cut across both cones, or this time, if your paper essentially is aligned up and down, kind of with the axis, you get what's called a hyperbola. So it's almost like having two parabolas together. So those are your basic conic sections. So now, how do we kind of tell them apart based on their equations? Well, first off, let's start with a parabola. Okay. Now remember, the parabola has an equation to be written like this. Now, it may not be often written like this, but it can be essentially written in some way like this form. The main thing to take away here, as I say, the key feature is a parabola, either the x term or y term is squared, but not both at the same time. So in this case, I have the y squared, the y term squared, and the x term not squared in the first power. In this case, the other way around, the x term is squared and the y squared, and the y is not squared. So if just one, either x or y term is squared, but not both, that's going to be a parabola. So let's take a look on Desmos and do some quick examples. Just remind you. So of course, the most basic parabola one usually start with is y equals x squared. Now, if I change this and instead make the y squared, I get a parabola resting on its side. Then also if I make one negative or positive, it just simply switches the sides. And the same thing, I can also negative switch up or down on the regular parabola. Now, you can also have parabolas written in other different ways. We can have something like, for example, y equals, even written like this. Let's say x minus 3 squared plus, let's say, 2 times x minus 4 equals 2, or something like that. So basically, what that is, it's still, you expect to be a parabola looks like that, so 100. Trying to come up with something that closes. Basically, that still comes up with a parabola because one term is squared and the other one is not. This just ends up kind of being a long, really long, skinny parabola. Okay, so that's what a parabola is basically in the case where one is squared and one is not. Okay, let's go back to our conic sections, that's a parabola, so one is squared and one is not. Now, a circle we're also, of course, familiar with. The key features of circles, any circle will be written basically like this. And what we're going to have here, I'm calling this A and C. So C is this number by itself here, and then A is the coefficient. And the key features of a circle are that the coefficients from the X term and the Y term are the same. And also the two terms, both are positive. This A is positive here and here, and this C is positive. And these coefficients numbers from the X and Y terms, which are both squared, these terms in front of each, the A's, are exactly the same. That's what distinguishes a circle. So once again, both X and Y terms are squared, which they are. The coefficients numbers in front are both the same and also both positive. Now this C here, it says the C also has to be positive. Turns out if C equals 0, the graph is actually a single point. And if C is negative, then there's actually no graph. Let's take a look at that with Desmos. So let me just erase this. Let's do a basic one. So let's do a very basic circle to demonstrate this. X squared plus y squared is equal to 1. Okay, that's a circle there. All right. Now, what happens when we make that 0? Make it 0, essentially it shrinks it to a point. Okay. Essentially, this number over here determines how big the radius is. So actually, if I replace it with a slider, and let's actually make the slider go from 0 to 5, for example. What I can do is actually see that as that value increases, as this number on this side increases, then the circle gets larger in radius. And if I go down to 0, it just actually shrinks down to a point, to a single point right here. So basically, if you make your circle diameter essentially go to 0, essentially shrinks it down to a single point. Now, once again, I can do that as well. So just this out one more time, make that 0. Okay, just get a point. Well, if I make it a negative number like -1, well, actually, there's no graph at all. There's no way you can have essentially a negative radius. Because remember, this side has to be, this side is actually the radius squared. And so that the only way to have a number squared to be negative would be make it imaginary. And so we're not looking at imaginary numbers here. So that would actually be no graph at all in that case. Okay, now let's go to an ellipse. So what makes a circle different from an ellipse? Setup is very similar. So both your X terms and Y terms are squared. Everything here is positive, but these numbers in front, A and B, have to be different. That's what makes it an ellipse. Okay. And remember, a circle is kind of a special case of an ellipse where A and B are the same. In this case, A and B are different. That's what makes it an ellipse. So once again, both X and Y terms are squared. Coefficients are different in front, A and B, and also both terms over here are positive. So let's go back and take a look at that again. So I can actually modify this. Let's just take a look at a 5. Now, if I change the coefficient in front of either one, make that a 2, for example, you can see that changes to an elliptical shape. Or make this one 2, that shrinks it or depresses it, in the X and Y direction, but it makes it an ellipse. And in a similar way, if I increase this, let's say to 10, or back to 5, or 20, it changes the size. So if I do a slider here, let's call this C instead. And I can make it larger by making C bigger or smaller. Basically contains the same type of shape, same proportions. And then once again, if I make it equal to 0, same way, if that's 0, it shrinks it to a point in the same way. And then if I make it negative, there's no graph because it's not possible to have a graph like that that's negative. Okay. Now let's talk about a hyperbola. So a hyperbola has, once again, a similar equation to an ellipse. So basically, a hyperbola is, and actually, let me take this, the coefficients. Actually, I should say here, let me actually normalize this. Really, this isn't quite correct. So once again, like an ellipse, both these terms are squared. The coefficients from the X and Y terms can be different, but don't have to be. So I'd say can be different. They don't have to be different. But the main thing is they have different signs. Assuming the C here is positive, let's leave that, it can be written that way, it's positive. these have to have different signs to be in a hyperbola. Okay, so remember, hyperbola is this conic section that looks like this, where essentially it's like two parabolas opening away from each other. Let's take a quick look at a hyperbola and some different kind of hyperbolas you can get. Let's go back to Desmos. Let's actually just modify this. So if I just make, well, first off, let's go back to say, let's make this 5. Okay. Now, if I simply make this negative, or one's positive, one's negative, what I get, that's a hyperbola. Now, if I make the other one negative, make this plus, and then make this one negative, you can see it changes the way it opens. Okay. And also the coefficients in front can be different. So if I make this 2, for example, and make this negative, then that simply changes changes the shape of it somewhat, but still it's still a hyperbola. The main thing is, once again, assuming this side here is positive, these have opposite signs over here. And the coefficients in front can be the same or different. Okay. Now, also in a similar way, let's see what happens if we try and make it 0. It turns out it looks like two straight lines crossing each other, and also make it negative, then actually get a hyperbola again. So basically, the only time you don't get a hyperbola is if this is actually 0. Okay. So let's go back to our drawings. Also do a few more complicated ones. So let's actually just blank this one out for a moment. What if we have something more complicated like this? Let's say we have 3x squared minus 5x, say, plus 2y squared plus 4x equals 6. Okay. Now, this turns out to be an ellipse. How can I know that? Well, actually, in a case like this is a bit different. What you could do is, if there's a method of completing the square where you can actually make this look like the ellipse we saw before. You can actually make it look more like this by a method of completing the square. I'm not going to show you that in this video, but that is possible. How can you tell what it is? Well, this is a little bit harder. This is where it actually is useful to graph it. Sorry, I'm actually hit the wrong window. There we go. This is where it's actually often useful to graph these things, because often it's hard to tell sometimes without looking at what it is. The one thing here I can tell, this is actually going to be an ellipse, because actually my coefficients in front of the x and y are different. If I make them the same, so I'll make this a bit bigger, so 10, there we go. If I make these coefficients the same, that makes it a circle, okay? These coefficients from the x and y, those individual terms are exactly the same. If I have to make one negative, then actually that's where I get my hyperbola. So once again, kind of follow the same rule. So if both those coefficients directly in front of the x squared and y squared terms are the same, and both are positive, you get a circle. If they're both positive and one is different, so make this a 5, for example, you get an ellipse of some type. And then if one or either is negative, then you get a hyperbola. Okay, so to wrap up a bit what we've seen so far, sorry, go back to this. So in review, we have the 4 different conic sections. Depending on how you cut across these 2 cones, you get these 4 different conic sections. And we talked about the main features of each one, things that kind of distinguish one from the other. So parabola, either x term or y squared is x term or y term is squared, but not both at the same time. A circle is basically both x squared and both x term and y terms are both squared, and the numbers and the coefficients in front are both the same, and they're both positive. Now, if they're have an ellipse, much like that, the only difference in ellipse and a circle in this case, if those coefficients are still both positive, but they're different coefficients, that makes it an ellipse. And then finally, if either's coefficients in front are negative, both x and y terms are squared, if either is negative, that makes it an ellipse. They can also be the same or not, but they are negative. So yeah, so the coefficients can be different in terms of they don't have to have the same essentially magnitude or absolute value, but they must have different signs to be an ellipse. Okay, so hopefully this explains kind of an idea of how to understand if you have a conic section, how to know what type it is by looking at it. But often the best thing to do is simply to graph it on a website like Desmos that will actually then show you better how to interpret it and how to use it. Thank you. Have a good day.